The solubility of solutes is very temperature dependent. For gases dissolved in liquids, as temperature increases, solubility increases. On the other hand, for most solids dissolved in liquids, solubility increases as temperature increases. Basically, an increase in temperature always shifts the position of equilibrium towards the endothermic process. Usually dissolving a solid in a liquid is an endothermic process because heat must be absorbed to break the bond, to break down the crystal lattice. So if you have solid plus liquid giving you solutions, this is an endothermic process. So if it's an endothermic process, you may recall from Molarity principle chapter that heat is like being on the reactant side. So therefore we're saying if I increase heat, then this reaction is going to shift to the right to relieve that stress, and then it'd be more solid would be dissolving into solution, becoming more soluble. Any additional heat would shift the equilibrium to the right, favoring your endothermic reaction, causing more solid to dissolve. For example, more sugar dissolves in hot coffee than cold coffee. The process of a gas condensing to a liquid is always an exothermic process. So a gas plus a liquid is giving you solution is an exothermic process. So remembering from Molarty's principle, if it's an exothermic process, then we're saying heat is the same thing as saying it's a reactant. So we're saying in this case, if we increase the heat, this is going to shift to the left to relieve that stress, which then will mean we'll have less of it in solution. It will decrease the solubility of that gas. Any additional heat would shift the equilibrium to the left, favoring your reverse endothermic reaction, causing less gas to dissolve. For example, a warm beer goes flat faster than a cold beer. Henry's law states that the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas in direct contact with the liquid. This is expressed mathematically as S is equal to KHP, where S is the solubility of the gas, KH is Henry's law constant, characteristics of the solution, and P is the partial pressure of the gas. Basically, the higher the pressure of a gas above the liquid, the more soluble the gas is in the liquid. For example, if you have a piston, okay, and that piston is pushed down, well, that gas has to go somewhere because you're losing that space, and it ends up going more gas into the solution, which thereby increases the solubility. So if a piston pushes down on a gas, more gas will dissolve in the liquid. So if you increase the pressure, you increase the solubility. Another example, let's look at Coke. The fizz that occurs when a soda can is open results from the reduced pressure of the carbon dioxide over the liquid. What you're doing when you open up the can is you're decreasing the pressure, okay, which then decreases the solubility, and hence your CO2 comes out of the liquid, the solution. Concentration expressions are a ratio of the amount of solute to amount of solvent or solution. The quantity of solute, solvent, or solution can be expressed in mass, volume, or moles. The common ways to express concentration are molarity, molality, mass percent, and mole fraction. We've covered several of these already, but we'll cover them again, as well as the new one, which we need in this chapter, molality. Molarity, which is a capital M, of a solution is the moles of solute in a liter of solution. When we say liter of solution, we mean the volume of the solute and the solvent in total solution. Molarity is equal to moles of solute per liter of solution. A solution can be prepared to a specific molarity by weighing out the mass of a solute and dissolving in enough solvent to obtain the needed volume of solution. One thing to note is that volumes are temperature dependent, and sometimes if you get a variation in temperature, you need to use a different unit, which we talk about later, based on mass, because mass is independent of temperature. The mole fraction of component A, Ka, and a solution is defined as the moles of the component substance divided by the total moles of solution. Once again, it's of solution, which means solute and solvent. Mole fraction of A would be moles of the substance A divided by the total moles of the solution. Mole fraction is unitless. You can see moles cancels. So there are no units on your mole fraction. It's just a fraction of what's there. Also, the sum of the mole fraction of all components of the solution equals 1. So if you got the mole fraction of 3 species, if you know 2 of them, you can figure out the third one because they should add up to 1. The mass percent of a solute is defined as following. It's the mass of your solute divided by the mass of your solution times 100%. Some notes. The percent in your formula is a unit, like grams, etc., and not the percent key on your calculator. So don't hit that. You just take your mass of your solute, divide by your mass of your solution, and multiply that by 100. The unit of mass doesn't matter as long as the same unit is used. So you can use grams or kilograms. As long as that mass is the same unit, it cancels out. Mass of solution equals the mass of your solute plus the mass of your solvent. Once again, solution means both solute and solvent. For example, a 3.5% by mass solution contains 3.5 grams of solute per 100 grams of solution. This is important, so anytime you see this, we like to get it into ratios where we can cancel units. So anytime I see that percent, I can rewrite that as 3.5 grams of my solute per 100 grams of solution. So I can get it in my units that I can cancel, which we'll show you in the next example. How many grams of water are needed to prepare 425 grams of aqueous solution containing 2.40% by mass of sodium chloride? So we got to realize that means something in a ratio, so I'm going to have to rewrite that. That's basically telling me I got 2.40 grams of sodium chloride per every 100 grams of solution. That way I can use it in my dimensional analysis. We know that there's 2.40 grams of sodium chloride needed per every 100 grams of solution by the mass percent. Therefore, we can determine how much sodium chloride is in 425 grams of solution as follows. So we know the mass of solution. We'll start off with our 425 grams of sodium, 425 grams of solution, and we're going to multiply that by our ratio, which we know there's 2.4 grams of sodium chloride for every 100 grams of solution. So by multiplying them, I cancel out grams of solution, and I can figure out how many grams of sodium chloride I need to make this solution. And that would be 10.2 grams of sodium chloride. However, we're not finished because I'm looking for the grams of water. This is the amount of sodium chloride we need in a 2.4% by mass solution of sodium chloride. However, we need to determine how much water must be added to obtain the 425 grams solution. So I know how much solution I want. I know how much sodium chloride I got to add. Well, the difference will tell me how much water I need to add. We know that of the 425 grams of solution, that 10.2 grams consists of sodium chloride, and the remainder is the solvent water. So the total mass of solution equals the mass of your solute, sodium chloride, plus the mass of your solvent, which is water. Rearranging this gives us the mass of the water is equal to total mass of your solution minus the mass of your sodium chloride. So what we did was subtract sodium chloride from both sides. Which gets us our new equation. Mass of the water equals the total mass of your solution minus your mass of your sodium chloride. So you get 425 grams of your solution minus your 10.2 grams of your sodium chloride means I need 414.8 grams of water. So to prepare 425 grams of a 2.40% by mass sodium chloride, it would require dissolving 10.2 grams of sodium chloride in 414.8 grams of water. Now, a note here, masses are additive, so I could just take 10.2 grams of sodium chloride and get another and on a balance get 414, add them up, and I naturally at that point have 425 grams of water. So masses are additive, as well as they're temperature independent. Okay, so sometimes we want to use it this way, that way I don't have to account for the temperature. While if I did this in volumes, since if I was doing this in molarity, I got a couple of issues. One, volumes are not additive. I can't add 10 milliliters of one substance and 10 milliliters of something else and say I got 20. That's an issue. Another issue to worry about is that volumes are also temperature dependent. If a temperature changes dramatically, then it's going to change my concentration as well. This is a new term and one we need for this chapter. The molality of a solution is the moles of solute per kilogram of solvent. So molality, and we use the symbol small m, is moles of solute per kilogram of solvent. Now here's a key change in any other unit, any other concentration term we've used has always been per solution, which is the amount of solute and solvent together. This is the first term we're using that it's only based on per solvent. Okay, that's key. It's kilograms of solvent. It's moles of solute per kilograms of solvent. This expression is useful in situations when concentration must be compared over a range of different temperatures. This is based on mass, the solute's mass, the solvent's mass, because it is based on mass, which is temperature independent, which is one that we tend to use when we start trying to calculate molar masses or freezing point and melting point, boiling point calculations. Let's calculate a problem dealing with molality. What is the molality of a solution containing 5.20 grams of glucose dissolved in 90 grams of water? Well, we know the definition of molality is moles of solute per kilograms of solvent, so we just need to arrange these units to get them to cancel out and end up with moles per kilogram. First, we convert the mass of glucose to moles and then the mass of water to kilograms. So moles of glucose would be your 5.20 grams of glucose times the molar mass of glucose. This is your molar mass. And we have it in the fashion to get grams of your glucose to cancel out. And that gives us 0.0289 moles of glucose. Then we do the conversion of our water. We got 90 grams, and we know there's 1,000 grams to every 1 kilogram. That way my grams cancel. I got the 1,000 in the denominator. Now I just got to place these two values into the definition of molality, which is your moles of your glucose in the numerator divided by your kilograms of water in the denominator. Remember that by definition it's kilograms of solvent, not solution, it's solvent, which gets us 0.321 moles of glucose per kilogram of water, which we term molality, small m symbol, of our glucose. Homework 71.